In this video, we'll be discussing the different types of maps and how we can show data on maps in different ways. The first map we have is the choropleth map, which is one of the most common types of map to show the thematic data. These maps use human-imposed administrative boundaries, which are zones that are established independently of the data. Typically, this could be country borders, provincial borders, or in this case, state and county borders. We can show both qualitative and quantitative data by coloring the zones using different colors. For example, we can see in the first two maps it is colored by the party who won the most votes in a respective state or county, which is qualitative. But in the third map, it is colored by the margin of victory by the winning party, which is quantitative. From these maps, we can see a lot of red, which covers the majority of the map, especially in the Midwest and South, which can infer that the Republicans won the election by a landslide, but we can see by changing the map type, we can change how the data is shown. To create these maps, we first select what administrative unit we will use. In this case, we'll use Ontario Census divisions. And then for quantitative data, we'll define bins, which are different ranges, and we'll give them a corresponding color. So for this example, our bins are under 14.5, between 14.5 and 15.5, between 15.5 and 16.5, between 16.5 and 17.5, and more than 17.5. We give each bin a corresponding color, generally a gradient. So in this map, the darker the red, the higher proportion of population. Finally, we color our geographic units based on the bin which the data falls within. For the next map, we have the proportional symbol map, which shows the location and magnitude of data with symbols. We can show qualitative and quantitative data together, where color may represent a qualitative data type and size is proportional to the quantitative data. We have three representations of the 2016 US election using proportional symbols, where the first two is the winning party by county proportional to the population of the county, and then the third one is the winning party by state proportional to the number of electoral votes. The difference between the first two is only the symbols used, where the first one has squares while the second one uses circles. We can see that this map paints a completely different picture from the choropleth maps, where the first two infer a large Democrat victory with winning in counties with high population, for example, urban areas where blue dominates the map. But in the third map, it demonstrates that the election was actually very close, as the election was decided by electoral votes. So scaling the states by electoral votes has the best representation of the election and what it actually looked like. A dot density map uses uniform, so basically constant size symbols to show quantities. Each symbol could represent one occurrence or several occurrences, such as one dot representing either just one person or 1,000 people. What a dot density allows for is to understand the spatial concentration of features, as areas with higher occurrences will be more densely packed with dots, while areas with less concentration will have more sparsely distributed dots. Looking at the two maps below, the first one is created by creating concentration of dots within each county, so that the distribution of dots is equal across the entire county. This gives us an idea of which counties have more voters. We can see the one on the right is essentially a dot per voter and where they live, giving us not only a population distribution map, but shows also how the votes are distributed across space. We can see that in very dense areas, voters typically vote blue, while in the suburbs and areas around the very dense areas, so more sparsely populated areas, they typically vote red. Contour maps are typically used for phenomena which vary smoothly across the map, which represent phenomena using isolines, which are lines connecting points having equal values. While these maps are typically used for natural phenomena like elevation, they could, although rarely, be used to show election results. We have isolines here showing areas of equal margin of victory. We can see that in the central US it has very high margins of victory for Republicans, while areas near the coast are typically won by Democrats. As mentioned before, we are more used to using contour maps for natural continuous phenomena such as elevation or weather, as every point in space will either have like a temperature, a precipitation, and an elevation, and they typically have gradients, meaning that the phenomena will be similar in nearby areas and more different the further away you go. Next up we have cartograms, which are maps which distort geographic area and shape in order to visualize the distribution of a variable. Geography is not necessarily represented accurately, but still tries to preserve some, so that the reader has an idea of the location of the variables. For example, in the US election map on the left, we have area distorted by population, making the rural states such as Idaho and Montana much smaller, while inflating the sizes of large urban centers such as Los Angeles and New York, which can be clearly seen on the map now. This paints a better image of the election, as election is not won by area but population. Therefore, distorting area by population makes it represent the amount of votes more accurately. The map on the right are states represented by hexagons, which correspond to their number of electoral votes and the party who won these votes. Since the election is decided by electoral votes, distorting the area of the states by the number of electoral votes gives a clear picture of how the election was played out. We typically see cartograms on transit maps, as since it simplifies geography, it makes the map much easier to read. For example, look at the simplification of Sea Island and Falls Creek in the Vancouver map. The bodies of water are represented now by rectangles. Since the transit writer only cares about getting from A to B, they're only interested in a station's location within the network, not the geographic space. Finally, we have the road map. While all maps we saw before are thematic maps, which focus on a specific theme, in this case the US 2016 election, road maps are not used to show data. Rather, it is a reference map tool which shows natural and cultural geographic features. The typical map we see on Google or Apple Maps is a road map, which helps us navigate by road and find important points of interest. Maps such as the one on the right, which contains topographic features, could also be considered a topographic map. To close off this presentation, we'll go over how to lie with maps. Going back to choropleth maps, by changing how we choose bin sizes, we can easily change how a map looks. For example, looking at the figure on the left, we can see that using the same data, but changing the bins for percentage foreign-born, we can completely change how we perceive the foreign-born population in Florida. If we look only at maximum breaks or equal intervals, it looks like there's only a significant foreign-born population in Miami. But if we use quantiles or mean standard deviation, it looks like there's a large foreign-born population all across Florida. With the example on the right, we have shown before how we can change how we see the results of an election just by using a different type of map. And here, Trump uses a choropleth map to emphasize the area won by Republicans, while in reality, he lost a popular vote in 2016 due to a high proportion of Democrat voters being located in dense urban areas. Moreover, it is difficult for humans to interpret magnitudes at higher dimensions, and it gets worse at even higher dimensions like the third dimension. This is shown on the graph at the left, where our actual perception of the size of symbols is lower compared to the actual area or volume for 2D and 3D symbols. This is exemplified by the example on the right, where all symbols are in reality scaled by 5 times, but is only actually perceivable for the 1D line. The 2D circle looks around 4 times scaled, and the 3D symbol looks around only 3 times scaled up, which is completely off compared to the 5-time scale up of both of these symbols. Another way we can change how a map is perceived by a reader is by using projections, which we'll go over in our next video. Thanks for watching.